In this problem, we want to find the gravitational force that's exerted on mass m3 by mass m1 and m2. First, I'll start this problem with a drawing of the situation. And I want to draw the individual forces that each of m1 and m2 would exert on m3. So gravity is an attractive force, and it pulls masses toward each other. So mass m3 is going to feel pulled toward mass m1. I'll call this force Fg1 on 3. Now let's draw the force of 2 on 3. Here's the force of 2 on 3. What we want to do is calculate the magnitudes of these forces, then break them down into x and y components, combine them into a net force, and then find out what is the magnitude and direction of that net force. Now we can just sketch this qualitatively with a parallelogram. We can kind of get a sense of what direction the total force will be. The total force will be something that looks like this. I'll call it Fg total. It's the sum of the two. All right, so one of the things you might start with in a problem like this is just saying what we're going to do, which is we want to find the total force as a vector by adding the two individual vectors. But because they're vectors, they have to be broken up into components, and there's a number of methods for doing this. I'm going to choose to break it up into two separate equations, where I find the Fg total in the x direction by adding Fg1 on 3x plus Fg2 on 3x. And then I'll have a totally separate equation over here for the y components. Fg total in the y direction will be the sum of Fg1 on 3y plus Fg2 on 3y. Okay. Now, anytime we're finding an x component here, we're going to need to know the magnitude and the direction of the original vector. So we're going to want Fg1 on 3's magnitude. We'll multiply that by the cosine of theta 1 on 3 in standard position. We'll need the magnitude of 2 on 3, and then we'll do the cosine of that angle in standard position. Okay, for the y components, we'll need Fg1 on 3 magnitude, and we'll do the sine of theta 1 on 3 in standard position. And finally, Fg2 on 3 magnitude times the sine of the angle of that vector in standard position. Okay, so what exactly am I writing down here? Well, Fg1 on 3x would be That's this component, the x component of the red vector 1 on 3. Now FG2 on 3x is going to be the component of the lower vector in the x direction. So maybe I can write those in. The upper one is FG1 on 3x. The lower one is FG2 on 3x. Now let's look at the vertical dimension. This guy here is going to be FG1 on 3 in the y direction. And this will be FG2 on 3 in the y direction. The whole goal here is to just not have to worry about those vectors that are at weird angles anymore. Instead, we'll replace them with these components that are aligned with the x and y directions. And now these vectors here completely represent the original gravitational forces. That's what we're doing here. So let's find out what FG1 on 3, what that magnitude would be. I'm talking about the length of this vector here. To do it, we need Newton's law of universal gravitation. According to the law here, FG1 on 3, the magnitude of it will be g times m1, m3 over the distance between those particles squared. So let's take a look at the the grid here, and we see, let's see, g is going to be 6.67 times 10 to the minus 11. That's just a constant. M1 is 17 kilograms and M3 is 8.5. For the distance between them, we see that they're separated by a distance of 3 meters in the x direction and 0.5 meters in the y direction. So we could find that distance. R13 is going to be the square root of 3 squared plus 0.5 squared, which is 3.041. So let's plug that in here. All right, I get 1.042 times 10 to the minus 9 newtons. All right, so FG1 on 3 is 1.042 times 10 to the minus 9 newtons. Let's go ahead and plug that right in here. All right, we also need to know the angle of that vector in standard position. Now for that, we can use the reference angle formula. We'll do the arctan of 0.5 over 3. because we're using this triangle here. And we'll get this reference angle right there. .46 degrees. All right, but our theta in standard position for that vector, though, is going to be 180 minus that. You may wish to switch your calculator to scientific notation mode or engineering mode for doing these calculations. That way you can see what the scientific notation answer would be more clearly. Okay, now we can plug that in here. Great. Now let's find FG2 on 3. All right, so for FG2 on 3, we'll do G times M2 M3 over R2 3 squared. It's going to be 6.67 times 10 to the minus 11. M2 is 22. M3 was 8.5. And okay, we got to find that distance. All right, the distance between them two, I see that they're separated by 1.5 meters in the x and 1.5 meters in the y. That means the distance is actually going to be 1.5 radical 2 if you do Pythagorean theorem on that. And then we'll square that. Let's see what we get. .772 times 10 to the minus 9 newtons. All right, so what we'll do is we'll plug that magnitude in here. And we also need the angle of this red vector. So I can see just by eye here that the reference angle is going to be 45 degrees. It points in the third quadrant, so we're actually talking about 225 degrees. All right, and that's everything we need for the x direction components. That's going to give us this guy and this guy. Now we want the vertical dimension as well. So let's just use the same numbers that we found. Same magnitude, same angle, but we use sine now. All right, we'll calculate these. All right, for my net force in the x direction, I get negative 2.988 times 10 to the minus 9 newtons. And for my net force in the y direction, I get negative 1.78 times 10 to the minus 9 newtons. All right, great. So our last task here is to just find the magnitude and the angle of the black resultant total vector. Let's do the square root of the squares of the components. I get 3.48 times 10 to the minus 9 newtons for my final magnitude. Then to get that final angle, we'll just do the arctan of the y component over the x component. I don't need the times 10 because it's going to cancel. Reference angle is 30.9 degrees. However, we are pointing in the third quadrant here, so let's add 180 to that. 211 degrees. And it's done.